Okay, Barrett. Some parts of this I'm going to talk pretty fast and realize that you can read. And so there'll be some things that we've talked about in multiple classes that we're just going to say, okay, you already know that, and move on. We're going to be starting chapter 8 today, fluid mechanics. We're going to learn a lot of cool things about fluids and stuff that like your dad thinks about when he tries to build a hydroelectric dam for a village out in Venezuela. Um, Things about pressure, um, hydraulics. You get to learn about Bernoulli's principle and flight, and where you take two pieces of paper and you blow between them. The pieces of paper go closer together, not further apart. So there's tons and tons of stuff in here that's way applicable and stuff that you see all the time. And then some weird phenomena that you can just do that will be pretty interesting. We'll see some videos later about just crazy stuff. Crazy stuff. So if you got your book, find page 273. You can always pause me, get your stuff out, and then unpause me and keep going. Fluid mechanics. We're going to look at the first section today, the first part of it, and start with section 1. We got some our objectives on 274. Define a fluid. Distinguish a gas from a liquid, and determine the magnitude of the buoyant force exerted on a floating object or a submerged object. Hopefully, I won't get interrupted too many more times by whoever's getting a ride. What else we got here? Explain why some objects float and some objects sink. We'll be doing a lab next year that involves this stuff, sinking and floating, diet Pepsi versus regular Pepsi, and we're going to create a thing called I call a 7-layer burrito. Get 7 different liquids with 7 different densities, and one sits on top of the other one. So that should be fun, and it's kind of like just seeing what happens. Drop things then into the liquid and predict what level they're going to stop at, seeing if they have a density similar to those ones. Maybe you've thought about buoyant force if you've ever been to a port.
Caleb Snyder, are you anywhere on the scope?
You've seen written on the side of a big tanker, it has their tonnage, what that ship weighs without anything in it, and then it has some lines written on the side of the thing. It tells you like how low in the water it'll sit if it's loaded with that much weight. So you can tell from the outside how much cargo the ship is carrying and how much the ship carries. They call it like water displacement, how much it displaces, and we'll be talking about that today as well. So let's start with this, and this is the part I'll go through pretty quickly. I think you know what a fluid is. Fluid is something that flows. Fluid can be non-solid, it can be a gas, it can be a liquid. Okay, all it has to do is flow, and air flows through the room quite easily. If you've seen like a toxic gas or something, that cloud can spread around, it can move, so it flows. And if you have a gas that's heavier than air, like the picture on page 274 at the bottom, they got some stuff that they're pouring in there. They can pour the gas. They can pour it, and you can see it flow. So anything that flows is fluid. Both liquids and gases are considered fluids because they can flow and change shape. And then liquids have a definite volume. They fit they're the volume of whatever container that they're in. And you can't squeeze them, really. That's how hydraulic brakes work. You can't compress that liquid. Gases do not. Gases, you can squeeze them down and make them take up a lot less space by compressing them. We did that before with sticking your thumb over the plunger thing and squeezing down the gas into a little tiny space. So liquids have a definite volume, but gases do not, and you know that. The fun thing here is with this buoyant force. Buoyant force is when you put something in water, when you're playing in swimming pool, or when you're out in the ocean. And the thing that's going to tell you that you always feel lighter in water than you do out of water, it's buoyant force. The water is holding, is putting some pressure on you, some force on you, so it doesn't seem like you weigh as much. The concentration of matter in objects is called the mass density, and we got a simple formula for that. We measure it by taking the mass of an object and dividing it by its volume. This right here is the Greek letter rho. I use a capital D, but the book likes this better. That's what they use for mass density. mass per unit volume of a substance. So we compare how much stuff there is to how much space that it's taking up. Think about that for a minute. You think what kinds of things are really dense, what kinds of things are really not dense. There's a chart in your book, a table on page 275 that lists several things with their densities in kilograms per cubic meter, and you can kind of use that to compare one thing to another in their densities.
Mass density is the mass per unit volume of a substance. The SI unit of mass density is kilograms per cubic meter. Gold is among the densest materials found on Earth. A balloon filled with gold would weigh as much as 20 water balloons.
Who would do that though?
Water is the standard of density. It has a mass of 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. Gases are much less dense than liquids or solids. However, they can expand or contract with changes in temperature or pressure, so it is important to note the conditions at which a measurement is made.
Now, the thing here that she's pointing out, the magic thing here is water. Okay, if you've got water at 4 degrees Celsius, if you had a tiny little 1 centimeter by 1 centimeter by 1 centimeter container, you filled it full of water, that would weigh 1 gram. So oftentimes, instead of seeing this kilograms per cubic meter, that's hard to picture in your head, a whole like kilogram and a whole cubic meter. To think of 1 gram, like the size of a paperclip, or weight of a paperclip, mass of a paperclip, and that filling up 1 centimeter by 1 centimeter by 1 centimeter, that's how much it would take up. That to me is just a lot easier. And what that does is it cuts off this times 10 to the third thing. You just have a number like 1 gram per cubic centimeter. Like makes a lot more sense. So if it's less than that number, it would float or it would rise. If it's less, or it's a bigger number than that, like this one, those things would sink. Even if you had a freshwater seawater kind of mixture, like at an estuary where a river comes into the ocean, the freshwater stays on top, the seawater stays down below, and that's good for the animals that live there. They can have it if they live at different elevations there inside of that river, or even in a bay, they can do better at surviving one place or another. So ice or water is the key thing there. Uh, okay, buoyant force then is the upward force exerted by a liquid like water, like when you're in the bathtub or something, on an object immersed in or floating on the liquid. Buoyant force keeps the object afloat unless there's not enough buoyant force, the mass is too heavy, it's too dense, it'll sink. Here's a brick. What can you do with a brick?
Consider a brick that can be submerged in a container of water. As the brick sinks, the water level rises and water begins to flow through the spout into a smaller container. The total volume of water that is now in the smaller container is the displaced volume of water and is equal to the volume of the brick. The brick will experience an upward buoyant force equal to the weight of the fluid that was displaced. This is known as Archimedes' Principle. Legend has it that he thought of it one day when he spilled water on the floor while getting into the bathtub.
And then he said, Eureka! And he ran out naked down the street screaming like a crazy fool. Do you get that? If you didn't get that, you need to rewind this and look at that again. So if this is filled up to the top there and you drop that brick in, the amount of water that comes out has the same volume as the brick does that's submerged. You can then take that and say, what is the force weight of that water right there? The force weight of that water, that would be a downward force, is equal to the force that the water pushes up on the brick to make it seem like it doesn't weigh as much. Okay, they call that the displaced volume. And when they talk about ships, they usually say how much water does it displace in the ocean. And they use that to say how much upward force they need for that ship to float. They can take a gigantic ship made out of steel that weighs hundreds of tons, and it can float because it takes up a lot more space. It's got a really big volume. Even though it's got a big mass, it's got a really big volume so that it can float in water. It's pretty awesome. The Archimedes principle describes the magnitude of buoyant force. Any object completely or partially submerged in a fluid experiences an upward buoyant force that's equal in magnitude to the weight of the fluid displaced by the object. So we're going to find the difference between how much that thing weighs in air and how much that thing weighs under the water. That's your buoyant force. That's the force that's pushing up on uh, on your object. So I've got a setup that I had in the kitchen that you're going to want to look at, and I submerged a weight underwater, a mass underwater, and I did it with water, and then I submerged it under oil, and saw that the buoyant force was different because oil and water have different densities. Oil is less dense. If you poured oil into water, it would float on the top. It's less dense. So it pushes with less force, the oil does, than the water does on the weight. All right. So what if you start putting weight on something that's
A
floating?
raft that is floating is in equilibrium. That is, the net force on the boat is zero in the vertical direction. The downward force of gravity is exactly equal to the upward force of buoyancy. If we add cargo to the raft, its weight increases.
Oh, watch out.
The raft will sink downwards. As it sinks, the buoyant force increases due to the additional water displaced. The raft will once again be in equilibrium. More cargo adds more weight, which requires more buoyant force. Any object that is floating has a buoyant force on it that is exactly equal to the weight of the object.
Otherwise, it sinks.
It is possible
Oh no!
to sink a
Don't
raft
put that
if the
there.
total weight grows too much. To sink a raft,
Yeah,
the total weight of the
that was
raft
too
must
much.
be greater than the weight of an amount of water equal to the whole submerged volume. In other words, an object will sink in water if its density is greater than the density of water.
No kidding.
Buoyancy continues to act when an object is underwater. The apparent weight of the object when submerged is just the true weight of the object minus the buoyant force.
Genius. Okay, so don't put too much on your raft, or else you're gonna have to swim for it. For a floating object, the buoyant force then equals that object's weight. The more weight you put on it, the more water it displaces, so the greater the buoyant force. The parent weight then is what it seems like it weighs. If you get in the bathtub or if you're playing in the pool, it's how much you feel like you weigh. It's what the scale is going to say when the thing is submerged under the water. You can then figure out if you know what you're working with and you've measured these things, you can find out what the density of your substance is that you're sinking the thing in. So check that out. Think about that. For these over here are densities: density of an object, density of the fluid, the weight of the object, versus the buoyant force on the object. I'm not going to look at this sample thing. What you do want to look at is this in the book, and come in and check out what we did in the lab, so you can kind of understand that concept. This was the story of Archimedes. King gave some dude a bunch of gold and said, make a crown with it. The guy brought the crown back. The king started to suspect whether the guy used all of the gold or just some of it. So Archimedes did this experiment, submerged it to try to figure out if all the gold was really there or if the guy mixed it with something. If this crown has a density less than 19.3 grams per cubic centimeter, you got shafted, dude, and he needs to go kill some dude that makes crowns. Go find him, get his gold back. We never know what happened, though. The story never tells us the punchline. Did he steal it or did he not? We don't know. We just know that Archimedes is the guy that figured out how you could check on this stuff. So, yay for Archimedes. He's the boss. And yeah, this is just the sample things. There's our densities. That's in your book, so you don't need that. But that was a way to determine what was going on there. All right, that's that for that section. I hope you had an awesome weekend, and we'll talk to you in a month.